Assalamualaikum. In this video, we will talk about our system for BITI1113 artificial intelligence system, which is AI-based gesture recognition system for classroom communication support. My team members is Wan Nurin Shira, Nurhani Kamila, and me, Tengku Nur Azli. In a classroom environment, effective communication is the cornerstone of successful learning. However, for students who are deaf or mute, especially those who have acquired hearing or speech impairments later in life, adapting to gesture-based communication methods can be a significant challenge. Often, a communication gap arises. Some students may know how to read and write, but are unfamiliar with specific teacher gestures, while others may understand the gesture but have limited reading ability. This disconnect this disconnect can slow down the entire learning process. To address this, our project introduces an AI assistive system by using machine learning. The system recognizes simple foundational classroom gesture performed by a teacher and instantly converts them into text. This creates a vital bridge for students, allowing them to follow instructions in real time while reinforcing the link between visual gestures and written words, ultimately supporting both communication and basic literacy development in an inclusive environment. To address the communication gap we've identified, our project is guided by two primary objectives. First, we aim to develop a machine learning model capable of accurately recognizing simple foundational classroom gesture and translating them into corresponding text. Second, our goal is to assist deaf and mute students in understanding classroom instruction more effectively, while simultaneously supporting their basic reading skills through clear visual text representation.
Now, let's move to the scope of our project. We have defined three main boundaries, which is first, regarding the system goals. Our system uses image-based machine learning to convert teachers' gestures into real-time text. We are focusing on four specific target gestures, which is first, writing, counting, reading, understanding, which is represented by a thumbs up. Second, our methodology is straightforward. We use webcam-based image capture to classify this gesture and display the corresponding instruction instantly on screen. Third, we have clear boundaries and limitation. The system is optimized for a single user, specifically the teachers. It is designed for a controlled classroom environment with consistent lighting and camera setup. And importantly, our gesture range is limited to this specific instructional gestures only. This is not a full sign language translator. These boundaries ensure our system remains focused, practical, and effective for its intended educational purpose. For our tools and algorithm, we have five key components, which is first, our platform. We utilize teachable machines, which provides a streamlined, no-code machine learning development approach. This allowed us to build and train our model quickly without complex programming. Second, our technique and algorithm. We employ image classification powered by an automated convolutional neural network, or we call it as CNN, automatically extracts visual features like hand, shapes, and orientation to distinguish between the four gestures. Third, our data. The system relies on capture gesture image as the primary input for model's training. We collected this image using a webcam under controlled condition. Fourth, our hardware. We use a standard webcam for a real-time gesture image capture, making the system cost-effective and easy to deploy. Finally, the system function. The trained model analyzes visual pattern from the live webcam, feed and maps them to predefined text outputs for the student. This process happens instantly, ensuring real-time communication support in this classroom.
Hi everyone, my name is Wanu Ishira and I will now explain the technical aspect of our project. Starting with the model development. Each gesture classes contains multiple image sample capture with variance in hand position, distance and viewing angle to improve model generalization. The dataset was then organized into the respective classes before being used for model training. For the data equation phase, we utilize a standard webcam through Google's Teachable Machine platform to collect our image sample in the control indoor environment. I am proud to share that we successfully compiled a robust training dataset consisting of 2,391 image samples in total. To ensure a highly balanced dataset, we collected 599 images for the writing classes, 602 for counting. Next, 600 for reading and 590 for the understanding gesture. For future extraction, our system employs a convolution neural network, or we call it as CNN. This algorithm automatically extract meaningful visual pattern directly from the training image, such as shape, hand, and finger orientation. Now, let's move on to the live demonstration of our system. As you can see on the screen, our model use a probability-based classification approach. Now we start with writing. We write using our hand, shows that it was writing. Now we go to counting. Next, we go to reading, like we pray. And lastly, understanding, shows thumbs up. Okay, that's all. Thank you.
Now, let's look at our performance analysis and limitation. For performance analysis, our model achieved high accuracy and successfully recognized all four classroom gestures in real time. The use of CNN with transfer learning enabled fast and reliable gestures classification under controlled classroom conditions. High confidence score indicates that the extracted visual features were effective for distinguishing different gestures. However, we also have several limitations. Model performance may decrease under poor lighting, complex background, or when the gestures are performed differently by different users. The system currently recognizes only four predefined gestures, limiting its practical use in real classroom communication. A more diverse dataset is needed to improve the model's robustness and generalization. For future improvement, we plan to expand the dataset with more users and different environmental conditions, increase the number of supported gesture classes, and deploy the system as a web-based application for a real-time classroom use.
In conclusion, our project successfully demonstrated the development of an AI-based gesture recognition system designed to support classroom communication. By leveraging Google's teachable machine and a convolutional neural network CNN, we created a model that accurately translates four essential instructional gesture into text. The experimental results are very promising, with the system achieving a high validation accuracy of 99.5% and real-time prediction confidence score ranging from 88% to 100%. Ultimately, this project proves that accessible AI tools can bridge critical communication gaps in education, fostering a more inclusive environment for students who rely on visual instruction. Looking ahead, we aim to expand this system by broadening our gesture dataset, enhancing model robustness against environmental changes, and eventually deploying it as a full-scale web application for a real-time classroom use. So that's all from us. Thank you.